Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them to succeed in their careers and lives. Are you interested in earthquake resilience with mass timber? If so, you're going to want to listen to this week's episode, where Matt and I will be talking with Ben Moerman, a PE, Ph.D, and project structural engineer at StructureCraft. We'll dive deep into the world of earthquake resilience and sustainable construction. Ben shares his insights on how mass timber can enhance earthquake resilience and the challenges of working with this material compared to traditional options like steel and concrete. We're also going to discuss advancements in technology for earthquake-resistant structures and the integration of sustainability goals in construction. I'm your host, Rachel Holland.
And I'm your host, Matt Cardle. Let's jump into this week's episode.
Before we dive in, we'd like to recognize our sponsor for this episode, PPI, a leader in engineering exam prep for the FE and PE exams. PPI provides expert prep courses and study resources designed to help you pass the FE and PE exams the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. Check out PPI today at ppi2pass.com to see all the options available for FE and PE exam prep. Now let's dive into today's episode.
Ben, can you start by telling us a bit more about yourself and what you do at StructureCraft?
Yeah, sure. So I'm a project structural engineer out of our Abbotsford office. So that's about an hour east from Vancouver. And we've also got offices in Vancouver, Seattle, and now in Italy. But yeah, I'm mainly on the design side, looking at a whole variety of things. So yeah, I spent a good deal of time looking at mass timber office buildings most recently. And with those, they're not always in seismically challenging areas. We do work all over North America. But yeah, we've been looking at some pretty long span timber floor systems, so I got involved in that. Also on the lateral side, with my background having done a Ph.D. in earthquake engineering at the University of Canterbury, obviously I've spent a lot of time looking at lateral design. And so with projects that are seismically challenging, then I've been getting involved in those, which is lots of fun. And then also get involved just having some experimental background. We have an R&D department here, so I've been involved in doing some research and testing and with some connection tests and some floor vibration tests, that type of stuff. So it's quite a broad range.
So just for our viewers then, is StructureCraft is it a structural engineering firm, or when you say it has an R&D department, are you like the mass timber producers also?
No, so we aren't really timber producers. We're engineers and builders. We do have part of our company that produces DLT, which is a mass timber panel product. But really the core business is being design engineers and then also builders.
Okay, awesome. Yep. So how did you transition from studying engineering to specializing in such a unique kind of like the earthquake engineering at kind of a higher level?
Yeah, so my first step on that was I finished my bachelor's and then decided to do a master's degree right after, because I'm sure you guys experienced it too in the undergrad. There's only so much they can fit into 4 years. And the earthquake engineering side of things it's quite vast. And so I felt I wanted to do a master's to just specialize further. And then I worked for a little bit and just found myself really interested in seismic design and also saw mass timber as an up-and-coming trend. So yeah, I basically looked around for what graduate programs were very strong in timber and earthquake engineering, and basically narrowed it down to Oregon State University in Oregon, obviously, and then to University of Canterbury in Christchurch. And they've historically been very strong in timber engineering. Andy Buchanan was kind of the main professor heading that up. He's semi-retired, mostly retired now, but that school really was interesting to me just because they had some pretty significant earthquakes in 2010 and 11. So, the research there is quite progressive, and they have a real sober view of what earthquake damage actually looks like. And they have a lot of funding to actually pursue, pushing the industry forward in terms of improving earthquake performance. So, ultimately ended up studying there and doing my PhD in Christchurch.
So did you do that in addition to a master's, or did you do your undergrad and then the PhD?
In addition to a master's. Yeah.
Oh, okay,
so
wow.
I did my master's in Vancouver at UBC.
Okay.
It was a course-based master's of engineering. But yeah, I took some good courses and learned lots, but I still felt like could go deeper and wanted to really specialize and also do some big experimental tests, which I was lucky enough to do.
Awesome.
And what was the research that you did at University of Canterbury? I know for us, it's in Southern California. Yeah, we deal with a lot of earthquakes, and I just remember seeing a lot of the lessons learned, a lot of the code stuff coming from the earthquakes at Christchurch and the university as well. So yeah, what type of research did you do there? Seemed to be interesting.
Yeah, so actually the reason I was interested in it is because they had a pretty successful research program at Canterbury looking at some early post-tension timber systems. So post-tension timber frames and post-tension timber rocking walls, which are now being quite extensively studied in the west coast of the States years later. And so that kind of piqued my interest, and I saw like, oh, they're interested in low damage design and they're using timber, which, yeah, both really interest me. And so I went there thinking I would do something in post-tension design, but didn't end up choosing that. I was mainly focused on improving the lateral capacity of CLT shear walls. And that was just an area that I saw there was a lot of potential, because CLT, there's lots of new producers coming online, producing it, and it's pretty cost effective. And, practically speaking, they're say 4 to 8 inches thick, but the lateral capacities were still kind of on par with plywood shear walls. And so it's like, well, why are we using so much more mass timber, but we're getting like the same lateral capacity? And if your goal is to sequester more carbon, maybe that's a win. But if your goal is to also be efficient and you want to maximize your structural capacities, then really where I saw a lot of potential was one, using a lot higher capacity connections in CLT wall systems, and also ensuring that they fail in a ductile manner, because we're concerned about earthquake actions on our structures. And then also looking at different structural forms. So probably the better half of my research was looking at a type of coupled wall system. So it's with CLT wall panels and then steel link beams in between, basically taking the concept from reinforced concrete coupled walls, which have been so successful, and they're very practical in building layouts, and then plugging in the steel links from eccentric brace frames in between those two CLT panels, and creating a coupled wall in that sense. So yeah, overall improving the lateral capacity of CLT shear walls, and then to do that basically looked at testing with higher capacity connections, and then created that coupled wall system, and that involved a pretty large scale test at the end of it.
Are you seeing the experimental stuff that you researched there, all of those, are you seeing those being used in new buildings now? Like, how is that kind of translated into the real world and past the academia part?
Yeah, good question. Like, so in New Zealand, they're better positioned to incorporate new technologies in their buildings because their code is fundamentally more performance driven. Whereas in North America, we're much more prescriptive. So it does tie our hands a bit, unless we want to go the performance-based design route, and then there's peer reviews and different stuff. And there's just a lot more friction when you're trying to incorporate new technologies. So unfortunately, none of it has been used in North America yet. But in New Zealand, I know there's a couple projects designed by Engco there, and they used our research to support some mixed angle screw hold downs that they used. So quite high capacity connections using, up to say 1/2 inch diameter self-tapping screws. And the mixed angle thing is something that our research group looked at quite a bit. And there's also research by my colleagues, Justin Brown and Thomas Wright, and basically using screws in combination. So you have screws at 90 degrees and then screws at 45 degrees. And so the 90-degree screws, they can bend and deform in quite a ductile way, while the inclined screws give you really high stiffness. And so the combination of those two make them really practical for buildings in seismic regions. And so they've already used that down there, which is pretty cool to see.
Curious about, I'm obviously used to the design in North America. So in New Zealand, when they're designing something newer, maybe with mass timber, so their codes are more accepting? Is that is that more of like they still have to go through a performance-based design process for new things, or are they just more lenient and open to the research?
Yeah, so it typically does still involve a peer review, but the way their system is set up and how the engineers there are used to working is just more, it's just more standard to have that process set up. And so you have your peer reviewer on pretty early, and it's just more like normal practice. So it doesn't have the delays and maybe the rigor that we kind of view performance-based design with in North America.
Yeah. Now, what about with what makes mass timber good for earthquake resiliency? I know you mentioned that was kind of the basis of your research, but yeah, what aspects of it in terms of maybe some of the technology make it good for earthquake resilience?
Yeah, so it's very lightweight, and when you have a mass timber building, the floor systems will tend to be, it's tough to assign a specific number, but let's say half the mass of a concrete flat plate. And so right away, you're reducing your seismic forces just by cutting your masses down. So that's a big benefit. The second benefit of using mass timber for earthquake resilient structures is it's quite highly prefabricated. So for critical details, when you're assembling those, you can do those all in a shop controlled environment, which is really nice because, sometimes on site it rains like crazy, or it snows, or maybe there's not the best practices. So being able to prefabricate things and have really good control over the critical connections, that's a really nice feature. Another thing is with mass timber, you're going to be putting in steel or supplemental damping devices in as your dissipators in the system. And those will be really discrete elements. And so for low damage design, you have really good control over, where's my device going to go? How can I replace that in the future? And there's lots, you can have lots of creativity in the design in that sense.
Yeah, I remember attending some of the UC San Diego tests where they had that 10-story mass timber testing. And yeah, it was really interesting to see. You had the post-tensioned rocking walls that you alluded to earlier. And, as they were taking it apart, they just kept testing different systems with it. Like they had BRB frame systems inside the walls. And I think they're doing some other tests in Oregon. It's pretty interesting what all of the mass timber technology is trying to do with some of the seismic systems that I've never even thought about. So it's pretty cool to see that.
Totally. Even at Canterbury, like when we were doing our tests, we got a lot of value out of it because, usually all the damage was concentrated. Let's say for a cantilever wall that we tested, all the damage is concentrated in the screws. But we could, instead of taking the whole test setup down and then installing a new specimen, we could just pull out the screws. We went over about an inch, put the screws into fresh timber, filled the old holes with epoxy, and then we had another test ready to go. And the turnaround time was like a day or two, which, is pretty awesome for collecting lots of data. Yeah,
that's great. How do you take the principles of earthquake engineering and integrate it into your daily work?
Yeah, it's a good question. And to be honest, none of our active projects right now, or I should say projects being built, main projects we have right now are at Johns Hopkins University, at Princeton University. We have a T3 with Hines. None of them are in seismically demanding areas. We do have several projects in the pipeline, kind of in early design right now, where I am getting to do some earthquake design, which is nice. But I'd say generally, what I'm trying to do with earthquake design is first and foremost just looking at capacity design. And I just feel like we have control on the resistance side as engineers. The hazard side is our best guess, or not our guess, but the geotechnical folks, they do their best to predict the earthquake hazard, but there's so much randomness. And that was one thing I kind of take from my experience in Christchurch is the earthquake was just substantially more than what the hazard predicted. And there's a good line from one of the professors there. He said, no one told the earthquake what hazard it was supposed to be at. And so really the best we can do is design lots of resilience into our building. So capacity design is one thing particularly important in timber systems, because timber doesn't have any ductility inherent in it. It can crush a little bit and it has some ductile-ish failure modes, but when we generally think of ductility, it's steel that can deform and absorb energy. So really good capacity design on the connections is something that I keep a close eye on. The second thing is just controlling drifts. If we want to control damage, keeping drifts below the code minimum is beneficial. And so generally, if we're scheming up lateral systems, choosing one that's more stiff is often the right choice. And then also just for repairability. So for low damage design, like I was saying, with concrete having really discrete connections, we can fit devices and different low damage technologies into the system. So they do have a good shot of being repaired in the future after a damaging event.
And you kind of answered my next question that I wanted to ask in terms of timber compared to steel or concrete, pros and cons. It seems like you alluded to it in terms of, you mentioned that timber is not so ductile and rely on steel. But I think you kind of said that it's kind of more repairable as well. Could you go into maybe the pros and cons of mass timber versus the typical ones, concrete and steel?
Sure. Yeah. I mean, ductility is the main one. So really the only modes that timber is ductile in is crushing. So compression parallel or perpendicular to the grain. But for tension and shear failure modes, it's really quite sudden and there's no warning. So yeah, those are kind of the modes we have to watch for. And when we're designing our connections and stuff, So yeah, with the crushing, we can be, when we're doing our capacity design, we know that the crushing is pretty reliable, but there's sometimes where, if there's any chance of tension perpendicular to grain failure, we'll reinforce against that with fully threaded screws or these types of things. So that's one thing on the connection side. When you're looking at planar walls, we typically, if we're looking at like substituting a CLT in for a concrete wall, one big challenge is just that the in-plane shear stiffness of CLT is just substantially less than the concrete. So yeah, kind of watching for when we're using timber lateral systems, they'll tend to be softer. And so we got to really pay attention to that stiffness of the system and make sure we're not going over with the drifts. Using different system configurations can definitely help with that. So whether you're putting your CLT panels into a C shape or an I shape or coupling them with beams, that's how we can kind of combat that just lower inherent shear stiffness of CLT panels. Yeah, and then for steel systems, if you look at most steel lateral systems, there's only a specific element that's actually doing the ductile work, whether it's the brace in a CBF or the link in an eccentric brace frame. And so there's a lot of timber-based lateral systems where we can just take that ductile component from the steel system and plug it in around timber elements. And then we can get our ductility while still using mass timber where it makes sense.
I know you talked about, you have a lot of projects right now that are not in high seismic areas. Have you had any recent projects that really took advantage of your expertise in the earthquake engineering that, it influenced the design or the construction process or different things like that?
Mm-hmm. Yeah. So we have a really exciting one in Vancouver right now. It's just starting up, but it's a 14-story mass timber building. And yeah, I've been pretty heavily involved. That's been the bulk of my time the last few weeks, by looking at the lateral system, because, we're looking at all the options and seeing what makes sense. But I think this one could really suit a mass timber-based lateral system. And at 14 stories, it's just not something that's been done in an earthquake zone before. In Norway, they have some pretty tall all-timber buildings, but there's no seismic hazard there. And so when I was at the World Conference on Timber Engineering in Norway last year, there were some pretty cool buildings they took us around to see. And yeah, they solved it with some really big glulam bracing and different stuff. But just having awareness of what's been done before there is really useful. But having to contend with earthquakes in Vancouver area is more challenging. And so on the lateral side, yeah, I've been doing lots of modeling and scheming of different systems, whether it's steel braces or it's CLT shear walls or post-tensioning them or not. And yeah, I think we're getting a good handle on that project and steering it in a good direction. But I think it's one that really suits an innovative timber-based lateral system. So it should be pretty special, but yeah, like I said, it's pretty early design still, and but it's been a fun one because I've been able to really kind of steer it on the lateral side.
And that project is, did you say that's the tallest in North America at this point that would potentially use mass timber for lateral?
Yeah, it's to the best of my knowledge.
Okay.
Other buildings have done this height or taller, and then they use concrete cores or steel brace cores, this type of stuff. But we're looking at doing a timber wall system as one of the options. I think it is our favorite right now, but yeah, it would be the tallest with an all timber lateral system.
That's exciting.
Yeah.
Yeah, that's pretty cool. Yeah, I've seen the ones with the core, the concrete cores, but this one's going to be out of pure wood mass timber shear walls. And so I know it's still a relatively new material, at least in North America. What advancements in technology or software have you found beneficial? Because I feel the software needs to catch up, right? Maybe it's not up there with concrete or steel, but I think the software industry or the technology industry is going to play catch up. But what have you seen and what has helped you?
Yeah, so on the software front, I think I'm really fortunate to be at StructureCraft because we actually have an in-house software called Branch, and that handles a lot of our shop drawing production, and it has a lot of CAD features. It's being developed into also a tool for us engineers to use, which is really something that'll makes a lot more efficient. But it's difficult in our industry because with mass timber, there's not really standard connections yet, like there is in steel or reinforced concrete. Like this steel design is so nice because you can open your handbook and quickly design these connections. And so mass timber doesn't quite have anything like that yet. I think we're hopeful that Branch is going to be a good tool in that direction. On the analysis side, I mean, modal analyses are just pretty fast to do nowadays, especially with timber elements in software like RFM. They have their RF laminate package, which can do your CLT shell stiffness properties really quick. That's quite useful. And then on the research side, like doing any sort of experiments, I've found Python is super useful. I don't think I could have done my PhD work without Python. Helped me look at all my experimental data, helped me run OpenSeas models, like all the kind of script-based tools. Those are definitely super handy and speed up my workflows. But at the end of the day, it's still with that stuff, it's garbage in, garbage out type of stuff. And so there's really no technological replacement yet for just like a keen designer designing a nice detail. I feel like that's still the core of our industry.
We can't get taken over by a computer just yet.
Not yet, yes.
Yeah. What about switching gears a little bit and talking about sustainability? Obviously, like a big topic these days in the construction industry. And I'm curious how your work with mass timber, like your opinion on how it's contributing to sustainability goals for our industry.
Yeah, so we do design in all materials. So for projects we're on, we'll often look at a timber, a steel, and a mass timber scheme. We do build the mass timber schemes, and we're also quite innovative in that space. And so, when we're designing a building, it's usually the first principle we go by is make it as efficient as possible, because just generally reducing material volumes is the best way to it's the best way to reduce environmental impact. And then on the mass timber side, that's obviously where we have a lot of strength and have been quite innovative in the past and plan to continue to do so. But yeah, for clients like really interested in certain carbon targets or these types of things, I think we've gotten pretty good at building out a suite of like carbon accounting tools. And so for clients looking at, say, the three schemes we come up with, the concrete, steel, and mass timber, we've gotten really good. This is out of my wheelhouse, but we have experts in-house who handle this part of the project. And so I think we can present clients with really solid numbers on that front. And so they can see, the different carbon numbers for each system and kind of weigh that into their decision-making, which seems to be getting more and more important on the owner side.
I was going to ask when you were saying that, like how how significant does that seem to be in their decision-making process? Does it seem like it's getting like a heavier weight?
Unfortunately, I can only think of one project where I've been involved on and have good knowledge of that. But it was a pretty big tech campus that we were designing with several mass timber office buildings. But I can definitely say on that project, they were very interested in the carbon numbers of each scheme. And I feel like that was almost as important as cost on their list. So
what did they end up choosing?
Well, they're still choosing.
Oh, okay.
So I'll let you know. Yeah.
Okay.
I was curious about, because I don't know many design firms with a research and development. What is that used for, and how does that integrate into your projects? Because I feel like you could do all sorts of crazy stuff if you have a research and development aspect.
Totally. Yeah. And I think the intent is to do all sorts of crazy stuff. So at the moment, it's still quite small and it's growing. But to date, we had a research program looking at sort of moisture effect on screws and how it affects the withdrawal capacity. So that one we did in-house. We also had a project recently where we had some connections at the end of purlins that were a little bit outside of the code. And so we did some project-specific testing for that. But we have a strong floor on the side of our shop here. We have pretty substantial capabilities that we can do there. And for any destructive testing, that's kind of the capabilities we have. And then we also do quite extensive floor vibration testing for a lot of our projects now. We'll collect some data as we build it, and that informs the design on our following projects. So it's definitely part of the company that's growing, and I'm happy to be involved with. But we'll see where it goes.
Yeah, I'm curious to see who gets dibs on those, where it's just like, I got a project, we haven't tested this connection before. Can we just test it so I can give it to the city so they can get it approved? Does it work like that, or is it more of a long-term thing?
Sorry, can you ask the question again?
Yeah, I was wondering how long that process is, where it's just like they want testing, so you just do it, or is it more of a, we're testing vibration for a project that we're going to have 3 or 5 years from now? Or is it just, we got a problem, let's test this new connection out and get it approved. Let's do it in the next year.
Yeah, it's a variety. So for the floor vibration stuff, I mean, most of that is on a serviceability level. So that's more informing us for future projects. So we know kind of what acceleration targets we have hit in the past, and we can also calibrate our models to that. But we've also done more reactive testing. For example, there's a project where we'd just finished building it, and then there was a certain region of the floor that the new tenant wanted a higher live load. There's a lobby or something like that. So we had to strengthen some glue lambs. So then for the glue we were going to use for adding lambs and the process we were going to follow, we had to test that. So that was more of a reactive testing where we were able to do it in our shop, break it, make sure it has enough strength, and then go do it in the field. But what's great about having the internal R&D is we did all that on a really quick timeline. So it didn't affect the project schedule too much, even though the tenant was asking for, some strengthening of some areas.
Cool. And
That's
do you
awesome.
think this is my final question. What about the future in terms of all the seismic research, resiliency strategies for mass timber? How do you see regions of the world adopting that, and maybe what regions of the world can really benefit from it?
Yeah, I think, mass timber systems are very prefabricated. So, I see mass timber systems, they can be fabricated, packed up in a crate, and sent across the world to more or less wherever. We've done some projects in China like that. But I just think on the west coast of North America, it seems like a really good spot to be, at least for this type of research to be implemented. Because for North American mass timber, it's I think the Pacific Northwest is more or less where started getting hot first. We've got earthquake hazard, and there's a lot of good engineers on the West Coast that know what they're doing with mass timber. And so I think for implementing new technologies in the space, that's probably the place we'll see it first. Yeah. I don't know. Does that answer your question?
Yeah.
Okay.
Okay, so Ben, for our listeners, what would you say is your final piece of advice in terms of what would you tell engineers who are looking to maybe like get more focused and specialized in earthquake engineering, or just like the younger, newer engineering people? What would you advise them to do?
Yeah, I mean, designing the stuff is obviously the best learning, on the job learning, but for more generally, like I think earthquake engineering, the best thing people can do is to read about or watch past experimental testing on structural components in the system. Even better if you can test them yourself, but that usually involves going to do a master's or a Ph.D. But I think that's the way that design engineers can actually get a real feel for how the structure behaves and when connections actually break. Because code clauses do a good job of assuring that normal structures behave well, but getting into innovative systems or systems in really high earthquake zones, I think you just got to have a feel for how the real components behave, particularly with mass timber systems.
Yeah, that's great. I just have to add to that was the final question, but I just have to add that I took my honeymoon in New Zealand.
Oh, nice.
A long time ago at this point, but it was after the earthquake. And I have a buddy from college that went out there to work after the earthquake. So we met up with him, and
nice.
Still to this day, my husband and I are like, let's move to New Zealand. It would be so fantastic. So we had a really good time. It's a very cool place to be.
It's a good spot. Yeah. My wife and I, we almost stayed much longer than we intended. But
did you stay after your PhD? Did you stay longer?
No.
Okay.
No, it was kind of deciding, are we going to do another 4 years here, or are we going to move back right away? Yeah. Sometimes we kick ourselves a little bit, but it's good to be back in Canada. So.
Well, just, food for thought. But my buddy that was out there that we visited, they just moved back there in January, and they have 2 kids now that are
Is this Eric?
Oh, yeah. Do you know him?
Okay. I know Eric. Yeah.
Okay. Yeah. Him.
Yeah.
So
nice. Okay. Yeah. No, Eric's a good guy. And he knows mass timber too. So.
Yeah. Yeah. But it was just, I was jealous when he just up and moved back. I was like, oh, man, I need to be more courageous in my life.
Yeah. No, it seemed like a good opportunity for him. I don't know if it didn't sound like it's a permanent thing, though.
I mean, what's permanent? Everything's temporary. So.
True. Yeah.
Anyway.
So is
I know.
Just based on that, I was curious about New Zealand. Just is it? I see New Zealand. I see Lord of the Rings with the scenery, and then you have cities that are seismically resilient. Is that's my interpretation of New Zealand? Is that correct?
The South Island's a lot flatter than I expected, but there's still really nice mountains and good beaches. Yeah, it's a good place, and the people are just generally laid back and easygoing.
So nice. Yeah, everyone there was so nice. It was so funny because we flew through LA to come home, and it was the second we landed in LA, airport workers were yelling at people to queue up correctly, and we just kind of looked at each other. We're like, oh, we're back.
Yeah.
Everybody's mean.
Seems right.
Yeah, I know. It's funny too there because I was talking to Eric when he said he was moving back, and it was after, and he said they got a place near Sumner, which is sort of a suburb of Christchurch. It's right on the beach.
Yeah.
And he's like, yeah, no one wants to live there because it's a 20-minute drive to downtown, which is a crazy commute for Kiwis. But
wow.
Get to live across from the beach,
yeah. And it's a super cute little area. So anyway, we gotta go back and visit him again while he's there. That's my goal.
Smart. There's actually the World Conference of Timber Engineering next year. It's in Brisbane. It's not too far from New Zealand, so I think I'm gonna do New Zealand and then go to Brisbane next year.
Oh, cool.
Yeah,
that would be fun.
It's a good excuse to go.
Totally. Yeah.
All right. Awesome. Well, thanks for joining us.
Thanks a lot, Ben.
Cool. Yeah. Thanks. Good to meet you guys.
Yeah, it's good to meet you.
Mm-hmm. All right. See ya.
See ya.
Take care.
I hope you enjoyed the episode today. We'd love to hear your feedback. comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, as well as links to any of the resources or websites mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcast. Until next time, we wish you the best in all of your structural engineering endeavors.